Okay, good afternoon. Oh boy, now I'm nice and loud. So we're finished with boring learning how to program and scheme, and from now on it's all big ideas. And this week's big idea is functions of functions. Oh yeah, administrative announcement. This Thursday I can't be here for office hours. So see me Wednesday or make an appointment. Or wait till next week. This is a picture of the inside of the human brain. It's got this brick wall, and on one side of the wall are things, and on the other side are actions. And it seems to be pretty firmly built into the way people think that we make this distinction. For example, all human languages make a distinction between nouns and verbs. Nouns are things and verbs are actions. In computer programming, you're accustomed to seeing the same distinction in the form of data versus procedures. Data are things like numbers and character strings and arrays and so on, and you know what procedures are. So our job here this week is to knock down this wall. Some people just take to this easily, and some people find it a very difficult idea. It's the same problem, by the way, that makes freshman calculus a notorious stumbling block for a lot of people who've been doing fine in mathematics prior to calculus. People think that, the trouble with calculus is the chain rule is complicated or something, but that's not it. The trouble with calculus is that it involves learning about functions of functions, namely derivative and integral. Each of those is a function whose domain and range are functions. So the derivative of some polynomial or something is not a number, it's another polynomial function, right? And similarly for other kinds of functions. And we're going to be doing the same thing in the realm of computer programming. So one of the main purposes of functions is to be able to generalize patterns. So before we actually look at functions of functions, I want to take an example of generalizing patterns that doesn't involve functions of functions, namely the one on the screen, which involves procedures that find the area of various regular figures, such as a square, a circle, a sphere, and a regular hexagon. So if I say square area 8, I get 64. If I say circle area 8, so it's a square of side 8, and it's a circle of radius 8. And the answer is 64 pi. 64 pi, and so on. So all of these procedures have something in common, namely, the area is proportional to the square of the linear dimension. Right? So it's all something times r squared, some constant times r squared. For squares, the constant is 1. For circles, the constant is pi. For spheres, it's 4 pi. And for hexagons, it's 1.5 times the square root of 3. So what we're going to do is generalize this so that we can have one procedure called area that handles all of these. And in order to do that, we add an argument. So the original separate area procedures only take one argument, which is the linear dimension. This new general procedure area takes 2 arguments. One of them is the linear dimension, and the other is a representation of which shape we're finding the area of. So now I can say area square 5, area circle 5. Okay? So it's a very simple idea. In this case, what we're doing is representing the shapes as the constant that you multiply r squared by to get the area. So it's 1 for a square, pi for a circle, and so on. But the general idea here is if you have a whole bunch of procedures that are almost the same, you can generalize them by having one procedure that embodies the stuff that's the same about them and takes an extra argument that lets you distinguish among the different cases for what makes them different. Okay, questions so far? Okay, I think this is a pretty easy idea. The thing is, it's kind of a cheating example because we were lucky enough that for this example, we're able to represent the thing that's different as just a number. Right? The thing that's different between the area of a square and the area of a circle is just what number you have to multiply r squared by to get the area. So using numbers to distinguish cases, that's nothing very exciting. But what's exciting is that we can also use functions to have a much more general way to distinguish cases. So, oops. So on the screen here are two procedures, one that finds the sum of the squares of a range of numbers and one that finds the sum of the cubes of a range of numbers. So let me just show you how they work. If I say some square from 4 to 6, what I get is 4 squared plus 5 squared plus 6 squared, which I hope comes out to be 77. And similarly, if I do some cube of the same range, I should get presumably a bigger number. Yep. So that's 4 cubed plus 5 cubed plus 6 cubed. Okay, well, how do these procedures work? They're pretty straightforward. A and B are the beginning and ending numbers of the range. If A is greater than B, then there are no numbers in the range. Right? If A is equal to B, there's one number in the range, so that's not the base case. The base case is A is greater than B, there are no numbers in the range, in which case what I want to return is 0. If A is not greater than B, then the range contains at least A. So what I'm going to do is add up two things, namely A squared and the sum of the squares from A plus 1 to B. So this is a recursive procedure. The standard thing about recursive procedures is that in the recursive call, the problem gets smaller. So this may look a little strange that we're going from A to A plus 1 rather than A minus 1. But the sense in which the problem is getting smaller is that the distance from A to B is getting smaller. If B is bigger than A, every time we add 1 to A, we get closer and closer to B, until finally we pass B, and that's the base case. And similarly, some cube is exactly the same, except that instead of taking the square of A, we take the cube of A. Well, what if I'd like to be able to take the sum of any function of A? Sorry? Yeah, so I want to be able to put any function in here, that's right. So what we have to do is, again, generalize the pattern by adding an argument. So the two specific examples that you see have arguments A and B for the beginning and end of the range. So I'm going to say, oops, define some function A and B. And now it starts out the same. If greater than a B, whoops, I missed. Let's try again. Define some function A, B, parenthesis, if greater than AB, 0. Otherwise, plus. Now, here's where sum square and sum cube were different. They each take a different function of A. So now I'm just going to say whatever the function argument is of A, and then sum, and I have to put the function in the recursive call, A plus 1 and B. Close sum, close plus, close if, close define. Okay? So to use this, I need to give it a function as an argument. So let me define a function here. To start with, if I just say define square of x to be times xx, then I can say sum square 4 to 6, and I get the same answer I got before. All right. If I just want to take the sum of all the numbers in a given range, I can define the identity function of x to be x, sum identity function 4 to 6, and that gives me 4 plus 5 plus 6. Okay? Questions so far? Yeah. Can you pass in a primitive function? Yes, so that's a good point. I could have said plus from 4 to 6, taking advantage of the fact that plus with one argument returns the one argument. Yeah, that would work too. So I can take, the sum of the square roots of the numbers from 4 to 6, and that's 6 2/3 more or less. Okay. Yeah. How do you do that with a function you haven't defined yet? Good question. And for the next little bit, you don't. But we'll get to that in just a moment. Yeah, that's a very good question. Because that's the problem with what we've done so far, is it's a little awkward to have to say, define, some function of x that you're not going to use in any other context before we can use sum. But we are going to fix that in just a second. Other questions? Before we do that. Okay, so the notation here is so simple, it just sort of rolls off the tongue, at least my tongue, so that you may think you're looking at something very easy, but let me back up to show you, whoops, the thing that sometimes gives students trouble. And that's the distinction between this point right here, where we are invoking the function fn, and right here, where we are not invoking the function fn. We are passing the function itself as an argument in the recursive call to sum. Okay, so this is an example of the thing I said last week about parentheses are never optional. There's a big difference between just putting the symbol, which is a representation, the name for the function as a thing, versus putting the name in parentheses, which means we're actually calling the function. So the name by itself like this, we're using fn as a noun, as a thing that we're passing around, whereas when it has a parentheses around it, we're using fn as a verb. We're actually taking this action. We're calling it. Okay, questions on that? It's an easy thing to get wrong when you're not accustomed to doing this. Okay. Okay, so here's another example of a pattern. I have a function up here called evens, and here's how it works. it takes a sentence of numbers and it returns a subset of that sentence, namely the even numbers from the sentence. So how does this procedure work? Well, it's a con because there are three possibilities that we're going to look at. First possibility, which is the base case, is that the sentence is empty. There are no numbers in it at all, in which case there are no even numbers, and I should return the empty sentence. If the sentence isn't empty, then we look at its first word. So there's first of nums in there. And we're going to ask the question, is this an even number? So we could use a predicate called even question mark, but instead I just sort of spelled it out. I said, take first of nums, take the remainder on dividing it by 2. So that's going to be 0 or 1. And if it's 0, then first of nums is even. If it is even, then what I want to return is a sentence made up of two parts. First of nums, because first of nums is even, so I want to keep it in the result, and evens of but first of nums. So we take the rest of the numbers, call evens recursively on them, and we get the even numbers from the rest of the sentence, and we stick first of nums in front of that because it's even, and that's the whole result. Otherwise, if first of nums is odd, then I just return evens of but first of nums. I throw away first of nums. I don't keep it in the result. Questions about that? Yeah.
Do we have remainder as a built-in?
Yes, remainders are primitive. Yeah. Any questions? Yeah. Wait, say it again. It looks like problem 5 on the homework. Yeah. Yes, indeed. This should not look too unfamiliar to you, I agree. Okay, another example is eWords, which works this way. Takes a sentence, and it returns the subset of that sentence containing words that contain the letter E. So the test that we're making, it's the same pattern. Again, it's a three-way cond. First, check to see if the sentence is empty. If so, return the empty sentence. If it's not empty, we can look at its first and its but first. So let's ask if the letter E is a member of the first word. If so, then we want to keep that first word in the result and also keep E words of but first of sent. If there isn't an E in the first word, then we want to just return E words of but first of sent without keeping first of sent. Okay? And again, the point here is that the pattern is the same. So here's another example. This one takes a sentence and selects from it pronouns. Pronouns being defined as the words in this collection of words right here. I, me, you, he, she, it, him, her, we, us, they, them, I know there are more pronouns than that, but I was too lazy to type them all in. Note in passing that member question mark works two different ways. You can give it a letter and a word. It says, is this letter one of the letters of the word? Or you can give it a word and a sentence, and it says, is this word in that sentence? So we're asking whether first of word is one of the words in this collection of pronouns. And otherwise, it's the same pattern. So down here, we have the generalization of this pattern. All the examples, evens and e-words and pronouns, took one argument, which was a sentence. This procedure takes two arguments, the first of which is a predicate function. And the only difference between this and the previous examples is this part in capital letters. The way we make the test to see whether we should keep first of sent in the result is we call pred of first of sent. Okay? So in this case, the function as applied to some argument isn't itself part of the result. It's just a true or false that tells us whether we want to keep first of sent in the result. So I can invent new functions. For example, keep the words from this sentence that are numbers. Okay? So, part of what you're seeing here today is the particular examples and the notation for using a procedure as an argument. But part of it also is to get the big picture here, which is that the ability to use an arbitrary function as an argument to another function allows us to generalize patterns with great generality. We can generalize the generalizing of patterns. So it doesn't have to be just areas of shapes where the thing that determines the specific example was just a number. If we can use a function as the thing that makes it the specific example, that gives us a very, very, very general mechanism. Okay? Okay, now I can answer your question about how do we make new functions? Because we really would not want to have to say define e-word, question mark, word, blah, blah, blah. We'd like to be able to just create a function on the fly to use as an argument to a higher order function. Oh, let me back up about the name higher order function, where that comes from. A first order function, and this is sort of mathematics language, is a function whose domain and range do not involve functions. Like they're functions of numbers, for instance, are first order functions. A second order function is a function of first order functions. A third order function is a function of second order functions, and so on. That's where the order idea comes from. Generally speaking, we're not going to care about second or third or whatever. We're just going to say a higher order function is a function of functions. Okay? So that's the derivation of the name. Okay. So what we want to do is invent a way to have functions without names. This, by the way, is another piece of something that seems to be kind of wired into how people's minds work, is that we expect functions to have names. So that all through your mathematical career, the way we're told to define functions is something like this. Right? F of x equals something or other, where we're saying that this is a function, we're giving the formula for the function, and in the very same notation, we're saying the name of this function is f. And with this notation, there's no way to talk about a function without giving it a name. Well, it turns out mathematicians are just like computer scientists, and they find occasion to have functions without names also. And the way they do it, and you don't usually see this in elementary math textbooks, they say x maps to 2x plus 6. This funny arrow with a line in front of it is the maps to symbol. And it's the way you represent an anonymous function, a function without a name, in math speak. Footnote to that. Another reason freshman calculus is hard is precisely that they usually don't use this maps to notation when they want to talk about a function without giving it a name. All they do is they write down a formula like 2x plus 6. Right? So you say, well, 2x plus 6 is a boring example, but you say d by dx of, let's do this, 3x squared plus 2x plus 6 equals 6x plus 2, right? You see that all the time in calculus class. Well, this is very confusing because what is this thing? Well, it could be a representation of a number, right? If we happen to know that x is 7, this is the number 44, right? Or it could be the name of a function. And this sort of sloppy notation encourages students to get confused about whether we're talking about functions or numbers right now. And they do it because they think you would get freaked out if they said what they should say, which is d by dx of x maps to 3x squared plus 2x plus 6 equals x maps to 6x plus 2. Okay? Well, it's more writing, and maps to isn't on most people's typewriter keyboards and things like that. So that's why they do it this way. But in fact, people would find freshman calculus easier, not harder, if they did it this way. Yeah?
I don't get the difference. What's the difference? They're both functions of x.
He's saying he doesn't get the difference between writing it this way and writing it this way. There's no way that anybody can confuse this with the name of a number. Right? This is clearly a representation for a function and only a function. It can't be a number. This thing actually is the name of some number. We don't know what the number is until we know what x is. But this is the name of a number, but it's also being used as the name of a function. Encouraging you to confuse the two, to not recognize that numbers and functions are two different things. So for instance, one of the things that tends to confuse calculus students is that calculus instructors and textbooks and so on like to throw around change of variables a lot. You know, you get halfway through a problem with x, and then they say, okay, I'm going to start calling this y now because x is something else. Well, it's perfectly clear, isn't it, that y maps to 6y plus 2 is the same function as x maps to 6x plus 2. And we could do this change of name, and it wouldn't bother anybody. Whereas 6x plus 2, 6y plus 2, are those the same or are those different? Well, we have to sort of play back the history of this proof that we're doing to find out. So having a representation for functions that's unambiguously a representation for functions really helps clarify things, I think. So in computer land, we have the same distinction. Instead of this, we can say define f of x plus times 2x 6. But what do we say instead of this? What we say is, lambda of x plus times 2x 6. Lambda is the computer science version of maps2. It's a way of saying, I'm constructing a function whose formal parameter is x and whose body is 2x plus 6. Right? So I can say, for instance, keep. Let's see. Lambda of word. Alaska, thanks. So the function here is the first letter the same as the last letter? And I didn't have to give that a name. I didn't make a definition of it. I could just throw it right into the keep expression. So that's how lambda is used to make functions that don't have names. Yes? Yeah, I could say define some name or other of word, blah, 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 and then separately say keep. But here, I don't have to make up a name. And since the lambda, if you imagine this not interactively but as part of a program, the actual function body is right here in the keep instruction. I don't have to go looking through some other part of the code to find it.
No, I mean,
Could I do keep of define? No. Define doesn't return the procedure, it returns the name that's being defined. Yeah?
So can you define a function just using lambda?
Can you define a function?
Like you can say like define whatever.
Oh yes, thank you. Very good question. Instead of saying define square x times xx, I could equivalently say define square lambda x times xx. And that does the same thing. In fact, the first of those with the parentheses is nothing but an abbreviation for the second one. The scheme interpreter translates the first one into the second one when you type it in. So once you have that understanding, you can see that instead of thinking about two different versions of define, and the define both gives something a name and creates a function, define's job is to give something a name, and lambda's job is to make a function. That's what they're for. So why is it called lambda? I'll get hands in a minute. No particularly good reason. A while back, a guy named Alonzo Church decided to see if we could build up a mathematical theory of everything, starting with functions as the starting point. I don't know how much you know about the history of mathematics, but around the beginning of the 20th century, mathematicians were trying to get a very clear, consistent, logically correct basis for all of mathematics. And mostly what they used as the starting point was the idea of a set. So they start with axioms for set theory, and then from there they invent arithmetic and so on and so forth. And Church came along and said, well, I'm going to play the same game, except instead of having sets as the basic fundamental primitive idea, I'm going to start with functions and see if I can't invent all of mathematics that way. And he used various Greek letters to have various different meanings in his system, and the one that said create a function was lambda, and that's where the name came from. Yes? Yeah. Yeah, so we can have define I don't know. I'll just make up a silly example. Lambda xy plus times 2x y. So f of 3, 4, and f of 4, 3, and different. Okay? Yeah, that's why the formal parameter is in parentheses, because there could be any number of them. Other questions? Okay. By the way, the Greek letter lambda looks like this. That's a lambda. And from now on the board, I'll write that instead of this because it's easier. Okay. Oh yes, lambda is a special form, just like define and if and cond are special forms. Oh yeah, and now I have to tell you about first-class data. So in programming language literature, first-class data, or actually first-class data types, I guess, are ones that can be used in these four ways. The value of a variable, an argument to a procedure, the return value from a procedure, and a member of an aggregate. So numbers are first class in every programming language. You can always have a variable whose value is a number. You can use numbers as an argument to a procedure. A procedure can return a number as its value. And a number can be a member of an aggregate, meaning you can have an array or a list or whatever full of numbers. One of the guiding principles of Scheme is that any data type that's in the language at all should be first class. And that's not true about all programming languages. So many programming languages restrict the things that can be an argument to a procedure or the value returned by a procedure. For example, it's common that you can't, languages that have arrays as a data type, you can't necessarily return an array as the value returned by a procedure, some of them. Some of them have pointers to arrays, which is not quite the same thing. For us so far, the only aggregate we have really is the sentence, and members of sentences have to be words. But 2 weeks from now, when we talk about lists, you will see that procedures and words and sentences and numbers and all the different things that we've talked about are all first class. They can all be the value of a variable. They can all be an argument to a procedure. They can all be returned by a procedure. and they can all be members of aggregates. So the idea that procedures in particular should be first class is a big part of what we mean by breaking down the wall between things and actions. Okay, so I want you to get this idea of first classness in your head. It's a good thing to know. Okay, any more questions before I go on? Yeah. Why is lambda a special form? Because remember what special form means. It means that the sub-expressions of the expression are not evaluated before the expression itself is evaluated. So So suppose lambda were an ordinary procedure. Then when you typed in something like this, we would start by trying to evaluate this as an expression. Open paren, x, close paren. Well, what would that mean as an expression? It would mean invoke the procedure named x with no arguments. Well, that's not what we mean at all, right? There isn't some procedure named x that we're invoking. What about this? This one sort of makes syntactic sense. Times xx is kind of what we want to do, but we don't have a value for x right now. We're just creating this function. It's only when we call the function that x takes on some particular value. So if we tried to evaluate times xx, we would get error unbound variable x. Okay? So lambda doesn't evaluate any of these things. It just says, okay, I'm going to create this new kind of data, new datum called a function that's going to have x as a formal parameter and times xx as the body. Okay. Yeah?
When lambda is invoked with a value?
It's not lambda that's invoked with a value, it's the procedure that lambda returns. So yeah, if I say that of 5, then we do times 5, 5 and get 25, yes. Okay? Any questions? Yeah. Yeah.
So if we don't have to name any procedures, we don't have to use define anymore, right?
Right. The question was, if we don't have to have names for procedures, we don't have to use define anymore. That's true, but you would find it awfully inconvenient. If you're building a program, sometimes you're going to want to call a function more than once. And it's a lot easier if you have a name for it. However, I'm glad you brought it up. It indeed is the case that you could have a programming language based on only two things. One is lambda, and the other is the ability to invoke procedures. And given just those two capabilities, you can perform any computation. That would be a universal language. And indeed, that's the language of the lambda calculus. It has nothing but those two capabilities. If you do the extra for experts, you're going to be doing things like inventing arithmetic based on nothing but lambda and procedure calling, which is kind of fun, but weird. But yeah, it would be really, really unpleasant to work in a language like that, so you won't want to. Other questions? However, it's a nice language for proving theorems about, right? If you want to prove that you can't possibly write a program to do thus and such, it's nice to have a language that only has a few ways of doing things. So, yeah. Yes?
What if we say define x and then lambda of x? I'm sorry, define y lambda of x times xx. So when we
So y will be a synonym for square.
say y, we're going to get the pound sign closure, whatever.
Yeah.
So we're going to get the name of the procedure.
Yeah, it's just like up at the top of the bottom half of the screen, I did that with square. Define square lambda x times xx. And if I say square, it's a procedure. Okay? Okay. We only have 5 more minutes, so I'm probably not going to finish this, but I want to start it. We've talked about how a procedure can be the value of a variable. That's this thing about define square, lambda x, and so on. We've talked about procedures as arguments to procedures. That's what we did with sum and keep in the examples I did before. What about a procedure as the return value from a procedure? So let me show you my favorite procedure in the whole world. Define compose f and g. So compose takes two functions as arguments. And it's the body of compose is lambda of x. So compose, when it's called, returns a procedure of one argument that computes f of g of x. So how do we use that? Here's an example. Okay, so I said, define second to be the composition of first and but first. And in the definition of second, there's no x's in there, right? It's a computation entirely in the universe of functions. The only data in there is the functions first and but first. So it's a really, really concise way of building up sets of more and more complicated functions. Here's another example. So twice f is compose f with itself. And now I can say define fourth to be twice square. So the fourth power of 3 is 81. Okay, here's one of the standard examples of functions that return functions. So define, I don't know, 3 plus. Make out of 3. Now I can say 3 plus 7, I get 10. All right, so make adder is a function that takes a number as an argument, returns a new function that adds some fixed amount to a number. So this is how we do functions that return functions. All we have to do is put a lambda in the body, or something that returns a function, as the body of the function we're defining. And we didn't have to have any special features in the language for a procedure that returns a procedure as its value. Just having lambda and the fact that we can put a lambda expression anywhere, including as the body of some other procedure, gives us the ability to do this. Okay? Questions? Great. I hope this sort of blew your mind a little. See you Wednesday.